So, hi everyone, welcome back to our video series on fluid mechanics. So let's just quickly, in this video we're going to talk about the Venturi flowmeter and how it's related to the Bernoulli's equation. So this is one of the examples where we can apply Bernoulli's equation, this energy balance that we see right here. Okay, so this is the general kind of thing. Here we assumed incompressible incompressible flow. We have assumed the mass flow rate is the same. This is very important. And of course we assume friction is neglected. That's what we use to get our Bernoulli's equation. So now we want to talk about how it's going to be used to measure flow. So in the last video, I talked about this equation, where if we have a simple case where for the flow meter, we want the elevation to be the same. Okay, so we'll have this picture deleted that we can, let's say, visualize this pipe. Okay, so there will be flow coming in here and exiting out here. Okay, it'll be the same flow, and we'll have 2 points. Okay, point A and point B. Okay, so let's use Bernoulli's equation to talk about these points. Okay, so given that this energy relation holds between here and here, what can we talk about the pressure relation between A and B, and of course the velocity? Well, just by intuition, you will say that the flow that's entering A and exiting B is the same. But how can we, mathematically prove it? Well, yes, there's something called mass balance that we have to know. Okay, so what is mass balance? So in this pipe, the mass that's coming in through this red line A is the mass exiting through this red line B. There can be no mass so-called accumulating, because you can't squeeze any more fluid in. It's incompressible. Okay, but the basic idea is whatever mass you put in is whatever mass you come out. It's just conservation of mass. Okay, and of course the wall isn't leaky. It's not leaking fluid. It's not bringing in fresh fluid or leaking any of it out. That's our assumption. So the mass flow rate at A, sometimes they use this m dot equals to m dot B. So what this m dot means is the mass flow rate. If you see a v dot, it is the volumetric flow rate. If we have a constant density term, we have a constant density, rho v dot A equals to rho v dot B. What does that mean? Okay, mass equals to density times volume. If you have the same, density, constant density, then we can write it as such. Constant density. Okay, let me remove this underline. Constant density. If a constant density, I can divide throughout. Okay. Delete. Constant density. Alright. And of course the correct way to put it is this way. But if a constant density means rho A equals to rho B, then we get this. Now if we have an average velocity, okay, if we have an average velocity and cross-sectional area, we can write the volumetric flow rate like this. the velocity, average fluid velocity at A, times the area, that will give you the volumetric flow rate. Okay, so this is what is known, what I'm talking about here is known as the continuity equation. Okay, continuity equation. It means that the mass coming in and out, okay, mass is conserved. That's basically what it physically means. Mass is conserved, or in case of incompressible fluid, volume is conserved. So volume is conserved only if it's incompressible, so to speak, but mass is always conserved. I mean, in most of our engineering cases anyway. So right, so what can we say about the cross-sectional area for A and B? That is exactly the same. So for same cross-sectional area, area of A equals to area of B, the cross-sectional area A is cross-sectional area B, we get this. Very simple. VA equals to VB, and if VA equals to VB, we can easily conclude that the pressure divided by the density of A equals the pressure divided by the density at B, and if it's the constant density anyway, we'll just get PA equals to PB. It's not very interesting, but why did we go through all that trouble just to find something so, intuitive and common sense? And how exactly are we supposed to measure flow rate? Now, if you want to measure flow rate, you'll have to do something a little different. Maybe if you want to have a pressure variation between A and B, we'll need to change this. We'll need to change the velocity between A and B. And how are we going to do that? We're going to, instead of having this, we're going to have this instead. Now, I'm not going to draw very nicely. Well, let's say this, this is B. And I have to have this arrow here. Okay. I'm going to copy this and paste. Now, this is the concept anyway. So we'll narrow, we'll change the area, cross-sectional area at B. Now, if we're going to do that, how is our equations going to change? Well, the mass balance is pretty much the same, right? So we'll get the mass from the mass balance, we'll get this, and from the energy balance, we'll get this. And obviously, because the elevation between here and here is the same, there's no such term. So let's say we want mass flow rate. So m dot equals to rho VA equals to rho V dot A. Okay, mass equals to density times the volumetric flow rate, which is just this. So let's say we just want to find this. We want to find this velocity at A. So if we want to find the velocity at A, we have two equations and two unknowns. So we have VA and VB. Okay, and let's say we can measure the pressure difference. We know the density and we know the areas. Okay, so by designing, of course, we'll know the area at A, we'll know the area at B, and we can use some kind of pressure gauge or manometer or whatever. Okay. I'll just put this pressure gauge here. And you have a PA here and a PB. So we'll have two pressure readings, and we should of course know the fluid density. And if it's water, it's about 1000 kg per meter cube in room temperature at pressure. So that's what we'll have. So we'll just want to find an expression for the velocity at A in terms of the pressure at A and the pressure at B. So let's carry on. So I'm going to move the pressures to one side. So I'm going to minus this over. I'm going to shift this over. And I want to substitute this VB out. I want to get rid of it. So let's make VB in terms of VA. Okay, VB. Right, VB equals to A over AB times VA. AA over AB times VA. So if you're going to square it, that's what we're going to get. So I'm just going to square all the terms. It's a very slow way of doing it. Oops. Okay. So all this is going to get substituted by this fella. So only thing to do is to factorize these terms together. Put these terms together. Okay, so I'm going to bring this to the other side. Okay, so let me write I'm going to bring this to the other side. PB minus PA over rho. Now going to bring this to the other side. So we have a minus sign here, so I will just change this and this. Okay, so I'm going to subtract both sides by this as well. All right, so looks pretty simple. And now I'm going to factorize this VA square out. Okay, I'm gonna copy, cut and paste it here, and I'm gonna get rid of this. Okay, we're almost there. So I'm going to rearrange by dividing throughout by this factor on the right, whatever this junk is. It's not okay, it's not junk per se, but anyway, you get what I mean. So it is going underneath. I'm going to bring this over here. Then next thing, I'm just going to square root this whole thing over here. I'm just going to say VA equals to square root of whatever this thing is. Okay. All right. I think we are pretty much done already. We have an expression for VA in terms of this. So let me me do this. Let me get the half out. 2 and this here. And this is our classical Venturi Flowmeter equation. So we have this situation here where you have some cross-section area at A and cross-sectional area at B. Now, instead of having, a flat so-called constant surface area, we'll have this instead. Okay, and that will help us to have a pressure difference from which we can measure the pressure difference. We can measure the velocity, and when the velocity is done, we can just multiply by the area, cross-sectional area, and then we will get the volumetric flow rate. Multiply by density, we get mass flow rate. So that's basically how a Venturi flow meter works. And if you look at something like Perry's Chemical Engineering Handbook, so non-isothermal, where is that Venturi flow meter? Flow meter. Okay, when in doubt, use the search button. Okay, while waiting for that, let's continue. I think it should be somewhere here. There you go. Yeah, Venturi flow meter. Now in Perry's Chemical Engineering Handbook, Chapter 6, you'll find something like this. Here. This is from Perry's Chemical Engineering Handbook. You'll see a Venturi flow meter like this. So what they have here is a manometer. A manometer. So you should be already familiar with this. This pressure difference equals to rho g delta z. And from that we can find the pressure difference. So we find the pressure difference between 1 and 2 and the ratio of the area between 1 and 2. We will get the flow velocity on average anyway. And so this is how we find our flow rates using Bernoulli's equation. So thanks for watching. I'll see you guys next time. Bye bye.